Welcome back, folks. This could be the shortest one of the semester, I don't know. Well, we'll see. So this is letter B under Roman numeral 3, which is bonding and nomenclature. So I'm just going to go over the basic rules here. I wrote that in red up there, but you probably can't read it very well. There's a flow chart that you want to download. I think I mentioned that in the last video. Just make sure that you have that either printed off or in front of you while we go through this, because I'm not going to rewrite all the rules for nomenclature. The flow chart is meant to do that and show you how it's done. And once you kind of figure out the patterns and memorize the things you need to memorize, then you won't need the flow chart anymore. Okay, so let's go. Nomenclature is a system of naming. Those of you that are in biology, there's a nomenclature for naming organisms. You use the dichotomous keys. Linnaeus, the Swedish, I think, taxonomist, interesting guy there, has a lot of interesting things in his past if you ever want to read about Linnaeus. This is our system for inorganic nomenclature. Those of you that are moving on to take organic chemistry, there's a whole other set of rules there, and it's a lot of work, but this is the language of science, not just chemistry. This is the language of science, that when you say something, it means something very precise. It's hard to imagine a more universal language than scientific nomenclature, so it's really important to be precise. When you're not precise, things can fall apart very quickly. I think we're even seeing that with how we name viruses right now. This is, of course, not as sophisticated as that. So before we get started, the slides are there. There's almost nothing on the slides for nomenclature because it's the flow chart, just a bunch of practice problems which we'll do in class. I do want to point out a couple of things. Remember that there's certain diatomic molecules that you should know. That when I say hydrogen, nitrogen, oxygen, you automatically write H2, N2, F2, O2, forgot that one, and the halogens. There's two other on the slides. I'm not going to try to write them. In their elemental form, when I say the word sulfur, like if you have just elemental sulfur, it's a yellow powder. I can show you some sometime in lab if you want me to. And that's actually not just S, it's not just S, it's S8. It exists in this not flat octagon, but it's sort of this up and down octagon, and you can see the diagram on there. It's kind of cool, actually. That's elemental sulfur. And phosphorus exists in a little pyramid with a triangular base and one above it, and then bonds in between, covalent bonds in between all of them. So phosphorus exists as P4, sulfur exists as S8. Good things to know in their elemental form. Okay, the basics of inorganic. What are we expecting you to be able to do? If I give you a chemical formula, H2O, NaCl, CaCl2, MgO, CH4, C2H6, those are actually organic molecules. So, if I give you a chemical formula, you can give me the appropriate accepted chemical name, and vice versa. That's the goal. And what's nice is the rules for nomenclature follow the rules of bonding. There's a set of rules for covalent compounds and a set of rules for ionic compounds. So take a look at the flow chart. The first thing you do when you look at a chemical formula or the name is identify, is it covalent? Non-metals. Is it ionic? Metal and a non-metal. If you get that right, then you're at least halfway there. If you get that wrong, you just get the wrong answer. So I'm just going to do a few examples. Let's do simple ones. Let's do ones you already know. And let's do them like we do in class. I'm going to kind of wing this a little bit. Well, let's just do examples. I can just use this. That works. Let's do the answer you already know. Let's just follow the flow chart. Okay? You already know that's sodium chloride, but let's make sure you apply the rules. So you identify it as ionic. I don't have the flow chart in front of me, you have to do that. Follow it to whatever side it is. I think it's the left side. It doesn't matter. You name the first element. You just name it like it is in the periodic table. Sodium. This is Latin for natrium, by the way. In Germany, you'll see this would be natrium chloride. But that's why Na is used there. It's Latin. And then you use this name of the second element with an I, D, E ending. It's more for stylistic reasons. Saying sodium chlorine is like saying two separate elements. Saying sodium chloride means that they're bonded together. Just so there's no ambiguity. See what I mean? So sodium chloride. So not sodium chlorine. Fine. We haven't talked about this molecule. So take a second. Is that ionic or is it covalent? It's ionic. Potassium and oxygen. It doesn't really matter for the naming purposes that it's K2O, so it's 2 potassiums to 1 oxygen. Okay, so we call this, and look at the rules very carefully, potassium. Do we or do we not put a di in front of that? Do we call that dipotassium? Answer, no. You do not use Greek prefixes with ionic compounds. So these are, you do not use Greek prefixes for those. So this is potassium okay, this is oxygen. So is it oxygenide? That's really clunky. So we shorten oxygenide to oxide, again, for stylistic reasons. Okay, briefly, I'll explain this more in lecture. Why don't we say dipotassium? Well, this is potassium. It's going to have a +1 charge. Everything in group 1 forms a +1 ion. So you're going to have potassium with a +1 charge, and you'll have 2 of those. Oxygen, you might recall from before, has a -2 charge. I'm not going to do the whole electron thing before and after. So it's a 2-to-1 ratio. When we say potassium oxide, it has to be 2 potassiums and 1 oxygen. The ratio is implicit in the name, but you have to think about it a little bit. It's actually harder to go back this direction. Well, in fact, I'll do some of those. Let's look at something else. Well, let me look at just one more. So it's an opposite example. Ionic, okay, I'm using 3 ionic examples to start. Metal, non-metal, calcium, chloride. No di, not dichloride, because these are both -1. This is +2. There's 2 -1s. So again, the ratio is implicit in the name, but it's not explicitly shown because the charges of the ions tell you what to do. I'll do that in the reverse direction later. Well, let's look at some covalent ones. I kind of told you that ahead of time. CCl4, non-metal. This is carbon. Typically, we do not say monocarbon. Typically, we don't do that. So just carbon and 4, mono, di, tri, quad, what? What's 4? Flip over on the back of the flow chart, and there's the Greek prefixes that we use here for nomenclature are useful. So it's actually carbon, tetra, chloride. Most of those prefixes match up with like geometry. Tetra, penta, hexa, hepta, and so on up to deca. Know those 1 through 10, please. And that's covalent. Non-metal. Okay, so this one we have to say di-nitrogen okay, I'm going to do that. Typically with English, we don't put 2 vowels next to each other in a lot of things. It makes them sound clunky, so we actually call this tetroxide. Nice. Now, there are a lot of nuances to these rules, but if you can understand ionic versus covalent, no prefixes, IDE ending, prefixes, IDE ending, those are called binary inorganic compounds. I think that's what they're called. And they're monatomic. It's just one type of atom here, one type of atom here. They may have more of a ratio, but those are the basic rules. And let me just show you a couple of other ones here. Go in the other direction. We already did this one. Magnesium oxide. Okay, first off, it's ionic. That should be your first clue. Metal, non-metal. There are no prefixes. That should be your second clue that it's ionic. But what's the formula? Well, it's going to be something with magnesium and oxygen, but what's the ratio going to be? Do we know that? We have to think about it a little bit. You have to know the charges on these ions. Well, from before, I think we made the argument that magnesium has a +2 charge and oxygen has a -2 charge. So we just need one of each of those. The formula will be MgO. It would actually not be Mg2O2. You write it in the simplest ratio. So it's just MgO. I'm actually not going to do any examples. If I give you a chemical name of something that's covalent, it kind of tells you what it is. And if you see trinitrogen dec oxide, it's N3O10. Okay? It just kind of tells you what it is. Those aren't that hard. The ionic ones are a little harder. You have to back calculate or think about the charges and then put them together. Let me do one that's maybe a little harder. How about, well, magnesium nitride. I don't think we've talked about nitrogen yet. But things in the nitrogen group form a -3 anion. That's something we'll probably have worked out by now, by the time of this video. So nitrogen and everything else in the nitrogen group, when it forms an ion, they don't always form ions. When they form ions, it's -3. And magnesium is +2. We're probably going to do this in class a little more. How would you combine these two so that the charges cancel each other? Because the total positive charge has to be the total negative charge. And we don't typically do this, but there's no charge here. When you combine magnesium and oxygen, overall there's no charge. We don't write +2 and -2 in there anymore. That's wrong. We just write MgO, because when they combine, there's no charge. When sodium and chlorine combine, there's no charge. We don't do this. Don't write it like that. That's actually incorrect. That's confusing. So how do we combine? Okay, maybe you know how to do this already. What's the least common multiple from math between 2 and 3? How many positive charges would we need and how many negative charges to make these equal? Well, the answer is 6. We could take 3 magnesiums and that would give us +6. We could take 2 nitrogens that's +6 total. -6 total. Well, how do we write that? Well, we write that as Mg3 N2. 3 magnesium, +2 cations, 2 -3 nitrogen anions. And then we're done. Here's a cheap method for doing it. I don't really recommend this because it doesn't always work. Is the charge on one becomes the subscript on the other. A lot of people do that in high school. It's fine, it works, but there's some exceptions to that. So I wouldn't get locked into doing that. So that's the basics of nomenclature. There are some nuances here, which we're not going to get into in this video. The transition metals in the middle of the periodic table have variable charges. Sometimes they're +2, sometimes they're +4, so we have to do something to deal with that. Sometimes ions come as combinations of atoms, and they're called polyatomic ions, and they stay as a little bundle. We don't break them up. So we have to memorize some of those. So those are on the back side of the periodic table. We'll look at those. We'll look at the transition metals in class. So if you can take care of all of that before you come, then we'll do the simple ones quickly, and then go right to the harder ones in class. So good, that'll work.